So here we have a graph of motion. Again, we're going to look at the y-axis and the x-axis. And that should tell you that the y value is whatever's on the y-axis. That's the angular acceleration. The slope is going to be the change in the angular acceleration per the change in time, and that is meaningless. No meaning there. So the area is going to be the y variable times the change in the x variable, and that's going to be the change in the angular velocity. Careful, it's not the angular velocity, it's the change. So it describes the rotational motion of a certain object with an angular velocity of 1.8 radians per second when the counterclockwise direction to be taken positive. So something is this direction is the positive direction. What is the change in angular velocity from 2 to 3.6 seconds? I want the change in angular velocity. That's just going to be the area. So I literally just want the area from 2 seconds, okay, to 3.6 seconds. This area here. Now let's see this area and this area. So this area is the area of a triangle, 1/2 base. That's 0.4, and once the height is 3. And then so that gives you that area. So that's going to be that. And then the bottom area down here, I would also split into a triangle and a rectangle and say, well, this is 1/2 base 2.4 to 2.8 is 0.4, and then the height is -3. Okay, because any area below the horizontal axis, that's negative area. Okay, we do use it like that. And then this rectangle area, 2.8 to 3.6, the width of that is 0.8, and the height is -3. So you're going to add all these together. Luckily, these two kind of cancel each other out. So when you add them all up, this plus this plus this, you're going to get -2.4 radians per second. Okay, so that means it's going to be clockwise. Okay, because it's negative, right? What's the final angular velocity of the object? Is the object rotating clockwise or counterclockwise? Well, so the initial angular velocity, the initially is 1.8. And then what we can find is the area. That will give us the total change, okay, which would be the final minus the initial. So we can figure out the final angular velocity if we know the change. Now, it's not the change in part A, because part A was just 2 to 3.6, okay? The initial one's going to be over here. So we have almost all the area. We need to include this area here. This area is 3 times 2, which is 6, right? The height and the width is 2. So that's 6. So then this is going to be, the change in the angular velocity here is going to be 6. And then adding all this area is -2.4. And that's going to be 3.6. And that's going to equal the final angular velocity minus the initial angular velocity. I guess is 1.8. So then the final angular velocity is going to be 5.4 radians per second. And because it is positive, and they're saying counterclockwise is positive, it is counterclockwise because we have a positive value. What time is the angular velocity object the greatest during the motion? This is actually a little bit tricky, but we want to think about it as like it's starting off positive. What area is going to cause it to speed up is when we have more positive area. So the greatest is actually going to be right at 2.4 seconds because all of this area is positive. We're going to increase the angular speed. It's only when we get to this region down here that we begin to have negative area that's going to take away from that angular velocity, right? So that's why this is going to be 2.8 seconds. 2.4. Right at this point right here. Because the area, which is the change, is all positive. Once you start including this area, it starts beginning to decrease. What time will the object complete its first full rotation since t equals 0? So first full rotation, again, is when the angular displacement is 2 pi. Now, in this case, none of this quantity would have given you the angular displacement part. All right? Like we don't have any direct graph readings that will give you the angular displacement. So instead, what we have to do is we have to think about the angular velocity and the amount of time that it's going to occur for that to occur. Because I don't, like I said, the y value is the angular acceleration, the area is the change in the angular velocity. So we have to think about it. So first of all, one full rotation is 2 pi radians. Okay, so initially it's going 1.8 radians per second. So how long, just think about it this way. You can think of it as like kinematics because the angular acceleration is constant over this time. So you can use kinematics for that part. So maybe you would want to do that. That might be an easiest way to go. We say, well, I want it to be 2 pi. I know we start off at 1.8. Okay, the angular acceleration is 6. Now, and then I want to know the time. Now, if this time ends up being more than 2, then we can't use this necessarily, because if it ends up being more than 2, then we're in a region where the acceleration has changed. Remember, with kinematic equations, the angular acceleration must be constant, and it's constant because the y value is the same during that time interval. So this only applies if we get an answer of t is less than 2. Okay, because once we get to here, now the acceleration is changing. Okay, so let's take a look. What equation would relate these variables? Is going to be this equation. So you can get 2 pi is going to equal 1.8t plus 3t squared, 1/2 times 6 is going to give you that. And so then this is just a quadratic. So we can use quadratic formula, you can use a graphing calculator, however you like to solve this. I will, if you wanted to just do a quick one on a graphing one, I'll just show you what it would look like on here. Let's just make sure we are in radian mode. Oh, it doesn't matter because this is just, okay, so 3x squared, we're not doing any trig here, plus 1.8x minus 2 times pi, and I want to know when this is 0, right? So I'm going to graph this. Oh, look, that occurs right around there. Where is that on the... It's going to move over. I don't know. You can just estimate. It's about 1.18 seconds. So it's going to be between 0.8 and 1.2 seconds. This was a little tricky, okay? But that's how you would handle that. Quick correction on my last part on the work here. The angular acceleration, if I'm reading... I didn't read the y value. The y value of the angular acceleration is actually 3. So when we plug it in to the calculator to figure out this part out, this is, so the alpha was 3 instead, so this is 3 over 2 t squared. And so again, if you use a calculator to find an answer, and you could test different answers if you wanted to, but you could just figure out, like, you'll find that the time is between 1.2 to 1.6 here. And I'll just show you real quick on, say, Desmos, what it's going to look like. I know I used the TI-84 before, but just 1.5x squared plus 1.8x minus 2 pi. And you see the 0 is going to occur at, actually 0.339. Sorry, I said that wrong. 0.339, which is, let me double check real quick. Sorry, that's not right. It's not 0.339, it's 1.8. So then we have 1.533 seconds. So that means it's going to happen around, in part C. Part C is the answer there. Okay, because I get 1.33 seconds. T is equal to 1.3 something seconds. Okay.